All right, I'm starting now a new series of videos that tell you what do astronomers really do. So I've been asked these questions many times, so I'm gonna tell you and show you what we are doing in real life. I've seen some videos about this. I think they're super nice, but they are a bit stories, And actually, I want to show you without much preparation, but really just while I'm working, what I am doing. I work with galaxies, mostly distant galaxies. Sometimes I also worked with close by galaxies. The thing about distant galaxies is that you don't see these grand designs images, but you see little dots. So for some people it might be a bit boring, but actually there is a lot of information in these little dots, and it's very interesting because we can study how the galaxies were long time ago, and how they are evolving, and how they became what we see today. There are many ways to study the galaxies. What we're going to see today are millimeter images and spectra. What is millimeter? You surely have heard about something about light, and there are some names that you probably have heard: ultraviolet, X-rays, things that we are familiar with, everybody. So this is always light. Light goes from gamma rays, X-rays, ultraviolet, optical, or let's say visible light, which is the one that we can see with our eyes, and astronomers call it optical, infrared, another popular name, far infrared, radio. And between this far infrared and radio, there is a millimeter, so to say, light. Today, we see some data taken with a big telescope here in the French Alps. This telescope actually is a combination of 12, actually 11, and the antennas, 11 radio telescopes that work all together to watch the same object. They are watching at the same time, they are observing at the same time a distant galaxy, and then we are going to combine the light of these 11 different telescopes into one single data set, that you call it. It's gonna be a start of a series. This is a bit tough today. It's not the best start probably, but you will see many funny things. There are different colors. You will see colorful images, not what you might expect. And I show you what I'm doing, what I mean when I am in my office and staring at these things and doing things with my computer. See you later. And now we call one of them, let's say this galaxy is called G09b1, which is a very, very fancy name. We then have to transform these UV tables into something that we have to see. So basically UV tables are the data, but in Fourier space, which is UV plane. UV are to the different parameters like X and Y, but in the Fourier space. So let type UVT, let map size, this is how many pixels, and then we want a cell of 0.2 arc seconds each pixel, so the pixel size, and then go UV map. It transforms this UV data into a map, and then we would like to see, to watch it, go view, there we go. And these are our data. As you see, you will already be bored after a while. On the left, we have the map. On the right, there is a spectrum. So basically, these data are like a cube. For each pixel in the map, I also have a third dimension, which is the frequency. What does it mean? It means that I can see at different colors, at different light frequencies, what the galaxy is doing. The dot here is basically our galaxy, or what we think our object, let's say. Let's make it a bit bigger. And I can make a small polygon to just let it show me only the spectrum of this region. Here you see already in the spectrum there are some, it's very noisy, but there are some, let's zoom, regions like this. Well, it was better before, it was easier to see it before. Regions like this that has an excess of emission. This is called a line, all right? So each line, it's like, you know, when you burn salt, you will see a light that is yellow. If you burn something else, you may see a green light. And this is yellow or green because there is an excess of light at the frequency or wavelength where you see yellow or green. The same thing here, you don't see the colors because it's radio, so you cannot see it with your eyes. But there is an excess, and this tells me that this galaxy has some specific molecule that has a high abundance there and is emitting. So basically, like it's warm, for example, or I don't know, it's doing some transitions. So basically, it's changing its status from one, I don't know, excited state into a ground state or less excited state. They're simply like excited because, I don't know, the light is hitting them, and then they are like warming up, and then they're going down, or there are also other processes possible. I have to select all the regions without this line. So let's say I'm gonna select from here to here, from here to here. Here there is seem on the right to be another excess, another line. And also I'm interested to know what are the frequencies of this. Then we go out. Here I've clicked some button, and here it tells me all the various frequencies. 49, 389, 452, 497, and the two lines are 149.8 and 143.016. We can copy a bit of this information here for me for the future. Now we have to open, let's name again the second data set, each galaxy, each data set, and go UV map, and then go view. For the way these data are constructed, I don't know if you're really interested in this. I have the galaxy, it looks very similar, but now I'm looking at different frequencies. So I'm gonna do exactly the same, and let's see if there is any other interest. Oh, there we go. Look at this line. This is a huge, very, very clear line. And here probably there is something that is called an absorption line, because if you have gas that is emitting, you see something that is an excess. But maybe you have a flame there, and then you have gas in front of it, and the gas is obscuring, so to say, the flame only at the frequency of the excitement of this molecule that is making this gas, and then you will see a dip in the spectrum. And this might well be, I don't know, could also not. But anyway, so we have a line here, 159.3. And then we have also absorption, 165.75, and in between here we have I'm gonna tell you why I need this stuff. So why do I need them? Because now I want to make an average of all the channels, of all the frequencies where there is no line, because I would like to make a map of the galaxy with as much signal as possible, but ignoring these lines. All right. So to do this, I'm gonna use UV average. So I'll take this UV table, and I would like an output UV table, which is gonna have a different name. All right. And then I would like to average all these channels that I said before, right? So I'm gonna do from 49 to 389, from 552 to 497. And there we go. It has produced a fantastic map of the galaxy. Let's have a look. There is a script that does everything I want to do. Okay? This is my map. Squeezed. Now you see there are this kind of stripes here, right? So this is basically the equivalent of what happens when the light hits the telescope. Actually, it is that. So the telescope is an antenna. You now have to imagine, like, if you, for example, look at a famous light bulb through a very small hole in a piece of paper, which is called like a pinhole, and then you let it project, and then you put like there is your wall on the back, paper and light bulb. You will see that on the wall you have different rings. This is called the diffraction image of your light bulb through this pinhole. The telescope is the same, it's just a round aperture. Okay, the light is coming from everywhere, that's from infinity, because the stars or the galaxies are very far away, and it gets onto this circular aperture, and what happens is basically producing an image that is this, that has all these rings. Now we don't have in this case only one, we have this 11 dishes, so 11 telescopes all together. So instead of a ring, depending on where the galaxy is in the sky, it produces this kind of stripes. You see there is a big object here in the middle, which is like the center of your ring, and there are two brightish other dots here, which is like the first ring, and then the diffraction image. Then there are others that will be the second, third, and so on. These are the various how it looks like. It's an airy ring, what you see, if it's perfect. So this guy studied and it's called airy. So now what I'm gonna do is like put all the, and this is the light is basically spread over all this diffraction image. I would like to concentrate it all in my galaxy, let's say in an image of the galaxy that is basically collecting all the light. I don't want to waste and lose all the light because there is not so much. So I'm gonna now select the central part, which I know is the galaxy, where I know is the galaxy, or let's say I suppose, and then I'm gonna do some cleaning in Fourier space, which is done by this script, and there we go. It basically took all the light from the whole ring, which is not a ring, but anyway, you got the point, and collected it again and has put it back in our center part. And then finally I make a zoom, and this is fantastic image of our galaxy in at 2 millimeters of wavelength in the observed frame. The galaxy is very far away. There is a so-called Doppler effect, which we called redshift, and is so far away that the light that is coming is shifted to a different frequency or wavelength with respect to what it was emitted. Why? Because the universe is not stationary, but is expanding, and this expansion is like an ambulance that has come to you, and then its expansion has an effect that is similar to what you hear in ambulances, noise. So basically, when an ambulance is going away from your position, you will see that you will hear that its noise is right, has a lower frequency, so is deeper. When it's coming to you instead, is as a higher frequency. And then, oh, it's like or if you don't have an ambulance, you want to speak about that, it's like a car that is approaching, a Formula One car is approaching, and then it went away, all right? This is the Doppler effect for sound. We have the same with light, because the light has a finite speed, and the universe is expanding at the same time. So the object that is emitting the light is going farther away because it's expanding the universe, and the galaxy is also going, so then the distance is increasing with respect to us. Then the light is shifted to a lower frequency or a longer wavelength, as we say. So what we see here is light at 2 millimeter, but depending on the redshift, so on how far away is this object, it might have been, for example, emitted at, I don't know, 500 microns, so half a millimeter, for example, and so on. This object is very special. Actually, there are two objects. It could be that there are two galaxies that are so far away. Remember, always, I mean, we see just dots, okay? That are two galaxies that are interacting with each other, like the Milky Way and Andromeda. This big one could be Andromeda, like, but I don't know, at I don't know how many billion light years from us. And this small one could be the Milky Way, very far away. I mean, it's just an example. It's not that they are, all right? Like Andromeda or like the Milky Way. Or it could be also that actually the same galaxy, but there is another object in between, much closer to us, and is bending the light of the galaxy that is behind it. This is called gravitational lensing effect. Actually, it was what we were looking for here. And I'm gonna talk about it to you maybe another time. I've started this since not so long. Before this, I was dealing with much funnier things. No, I'm kidding. I should not tell this. With optical, infrared, and so on. And this will be a matter of something else, some other lesson, because now probably I filled your head with a lot of things. But thanks for watching. Have fun and enjoy.